Okay, YouTube, in this video we're going to focus on graphing a polynomial function, and I just want you to know this is kind of a rudimentary approach to graphing these. We're going to add more steps into our process as we learn more and more about these functions, but for now I want you to know that basically when you graph a polynomial function we could break it down to these essential steps. And so number one is always going to be this, determining the end behavior of the graph. So what our graph behaves like on the ends, and recall that in terms of end behavior we can look at our last diagram here, but the possibilities are either that it rises both on the left and the right, or falls both on the left and the right, but the end behavior is the same on left and right, or the end behavior is different on the left and right. So there are four possibilities here for end behavior. And in order to determine what our end behavior is going to be, we'll always just look at the leading coefficient and the degree. So I notice that the degree here, I'm actually going to take the time to list this here. We say the degree is a third degree situation here. I'm going to write a little note. This is a cubic, if that fills in there. And then we'd also say that the leading coefficient here, the leading coefficient looks like a positive 1. I'm going to write a little note here that this is positive and that this is an odd degree. So in terms of end behavior, I know that because the leading coefficient is a positive thing, that on the right side of my graph must rise. And I know also because now that it rises on the right-hand side and that my degree is odd, the left-hand side behavior must be opposite its right-hand side behavior. So I know that it falls on the left-hand side. So in terms of end behavior, I've listed it on my graph here, and I would recommend you do that before you try to fill this in here. But we say as x goes to negative infinity, as we go to the left, my y values will go to negative infinity, they'll fall. And then we'll say as x goes to positive infinity on the right, my y values are going to go up to positive infinity. So there's our end behavior right there. So we've determined the end behavior. Number 2 says this, create a table of values by plugging in x values into the function. Well, these x values are really just common. I want you to know that polynomial functions are not all going to be interesting between x equals negative 2 to positive 2 going by whole values. Okay, sometimes we would plug in 7 all the way out to 15 if we needed to, but what I'm going to tell you is because this is kind of just an approach to graphing polynomials, know that for right now you can plug in any x values you want, any of them, to get some more y values on your graph. It's just that we want to find the interesting ones. So we've created our table here. We need to plug in these values. So we're going to use direct substitution. And I'm going to start by plugging in 0 because it's pretty quick, and I want to note something here. When you plug in 0 for x, you're really finding your y-intercept. We say this is the y-intercept. When you plug in 0 for x, we are finding the y-intercept of your graph, where it hits the y-axis. And also this, we would say that if we plug in f of 0, by direct substitution, what we're going to get is a situation where we have x cubed plus x squared minus 4 times x plus 2. And I'll just fill all these in with zeros. What you're going to see is that you get 0, 0, 0 here. You're left with the 2. So another thing that I want to fill in here is this. I want to make sure that we fill in this 2. We're going to make a little note here that the constant term is always the y-intercept on the graph. I just think it's really important. It's like when you graph a line, you have y equals mx plus b. That's an important point where it hits the y-axis. So I'm going to go ahead, I'm going to put 2 on this graph, 0, 2. I'm not going to label it because I have it in my table over here. As long as it's in the table, you don't need to label it, okay? And I didn't mean to rhyme that, but that's really dorky sounding. So let's plug in 1 here. If we plug in 1, okay, so 1. You get a 1 in all these gaps over here. If we plug this 1 in, what we're going to end up with here, it looks like, is we get a 1 plus 1 minus 4 plus 2. So we have 2 minus 4 plus 2. 2 minus 4 is negative 2, and negative 2 plus positive 2 is 0. So this is kind of cool, this point right here. I'm going to make a little note that this happens to be an x-intercept of this graph, x-intercept, because it is where our y value equals 0 when we plug in that x value. So we say 1 comma 0 is right here on our graph. And so let's see, plugging in 2, we could plug in 2 here. We're going to get 2 cubed, I'm going to cheat a little bit here, plus 2 squared minus 4 times 2 plus 2. And so we get 8 plus 4 minus 8 plus 2, or 12 minus 8 plus 2, or 4 plus 2, or, whoops, I was already thinking it, guys, sorry, 4 plus 2 is 6. So we'd say 2 comma 6 is on this graph. So we'll go right 2 and up 1, 2, 3, 4, 5, 6. Okay. So now let's go over to the left side here. We plug in negative 1. So negative 1 cubed plus negative 1 squared minus 4 times negative 1 plus 2. Okay, so when we cube a negative 1, we get a negative 1, but when we square a negative 1, we get a positive 1. And a negative times a negative here gives us positive 4, and then we say plus 2. So now these ones, they just cancel out, and we get left with a 6 over on this side also. So it must be at a height of 6 over here. And then we could say, okay, one more value we want to plug in here is negative 2. We get negative 2 cubed plus negative 2 squared minus 4 times negative 2 plus 2. You can see how plugging in points, you use a lot of scratch paper here. We'd say this is a positive 8 and this is a positive 2. So a negative 8 and a positive 4 here. That's going to give us a negative 4 plus 8 plus 2. And then we would say, okay, so negative 4 plus 8 plus 2, that'd be a negative, positive 4 plus 2, which we get 6 again, which is kind of a fun situation here because here's what I know. Now, the last step after we plot the points on step 3 here is connect a smooth curve from left to right that passes through these points and has the appropriate end behavior. The thing is, I've got to have a graph that passes through all of these points from left to right, each point one time, but it falls on the left and rises on the right. So what I can see is I can kind of imagine this graph that starts way down here on the left and comes up and must have gone through this point here and then had to come back around, because what it's doing is it's coming back around, passing through these points, and then it's going to turn here, and our right-hand side behavior of this graph must be up. So, if I wanted to do this in pieces, I could say, well, here I can see that it's just going to take off for good. And on the left-hand side, I can see that, maybe I'd plug in negative 3, but it must decrease after this. But what it does in between is it's got to pass through all of these points right here. So I would get some graph that looks something like this. And congratulations, you've graphed your first polynomial function here, the smooth curve that we knew its end behavior, we just needed more points on the graph. So just to show you how well we did, this is the actual curve that we see here. And we can see that at negative 1 and negative 2, in both spots here, it's kind of hard to pinpoint. At negative 2, looks like we went through 6. And negative 1 we went through 6, and we got a 0 here also on our function at, let's see, 0. I had this graphed. At 1 is what I have marked on our graph here. Maybe I plugged in a value wrong. No, let's see. 1 comma 0, so there's our 0. But yeah, that's how you graph a polynomial function. You determine the end behavior, make a table, plug in some more values, plot the points, and then make your smooth curve through all those points adopting the end behavior. Cheers.